Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Tonight's gentle journey takes us to the very beginning of everything, not just Earth, not just our solar system, but the entire universe itself. 13.8 billion years ago, something extraordinary happened. In a single moment, space and time, matter and energy, all of existence as we know it, burst into being. It's a story that stretches from the tiniest fractions of seconds to the vast cosmic structures we see today. But before we step back to that first moment, feel free to share what time it is and where you're listening from. It's oddly comforting to think that, no matter when or where you are, we're all made of the same cosmic ingredients, forged in those first miraculous moments. We'll wander through the hottest temperatures ever reached, explore the mysterious forces that shaped reality, and discover how the universe went from a tiny, impossibly dense point to the vast, star-filled cosmos around us. There's no need to follow every detail. Just let the ideas drift by like distant starlight, each one a gentle step closer to understanding our cosmic home. So settle in, close your eyes if you like, and let's take a slow, peaceful journey back to the very beginning of time itself. Every once in a while, someone asks a question so big it makes your brain feel a little dizzy. How did the universe begin? It's the kind of question that sends philosophers into deep contemplation and physicists into heated debates. Not because it's complicated, exactly, but because it touches something fundamental about existence itself. It's asking how everything came from nothing at all. Think about it for a moment. 13.8 billion years ago, there was no space, no time, no matter, no energy. No stage for events to unfold upon, no clock to measure their passing. And then, somehow, there was everything. The entire universe, in all its vastness and complexity, burst into existence from a state of absolute nothingness. It's like asking how the first word was spoken when there were no mouths, no air, no sound, and no one to listen. This question pushes at the very edges of what human minds can grasp. We're used to things having causes, to events following other events, in a nice, orderly sequence. Drop a stone, and it falls. Light a candle, and it burns. Every effect has a cause, every beginning has something that came before it. It's how we make sense of the world. But the beginning of the universe breaks this comfortable pattern entirely. What caused the Big Bang? Well, if time itself began with the Big Bang, then asking what came before is a bit like asking what's north of the North Pole. The question seems to dissolve the moment you really think about it. There was no before, because there was no time for a before to exist in. There was no place where it happened, because space hadn't been invented yet. There was no clock ticking down to 0 hour, because there were no clocks, no hours, and no concept of zero. And yet, here we are. You're listening to this, I'm speaking these words, and somewhere in the distance, stars are being born while others are dying. The universe is magnificently, undeniably real. So something happened, even if that something challenges every intuitive notion we have about how things work. This is where science gets both humble and bold at the same time. Humble because it acknowledges the staggering mystery we're dealing with. Bold because it refuses to simply shrug and walk away. Instead, scientists have crafted theories, run experiments, and built mathematical models to inch closer to an answer. Some of these ideas are beautiful, some are strange, and some sound like they were dreamed up by someone who'd had far too much coffee and not nearly enough sleep. But here's the thing about this ultimate question. It doesn't just challenge our understanding of physics, it challenges our understanding of existence itself. If the universe began from nothing, what does that say about the nature of reality? Are we living in a cosmic accident, a random fluctuation in some deeper field of possibility? Or is there something more purposeful, more elegant at work? Different cultures and traditions have grappled with this mystery for thousands of years. Creation myths speak of words spoken into darkness, cosmic eggs cracking open, gods breathing life into emptiness. These stories often share a common thread, the idea that something powerful and mysterious lies at the heart of existence, something that transforms nothingness into somethingness through processes we can barely imagine. Modern cosmology has its own creation story, and it's every bit as strange and wonderful as any ancient myth. It speaks of quantum fluctuations, of space itself expanding faster than light, of forces splitting apart like friends going their separate ways after a long evening together. It's a story written in mathematics and tested against observations, but it's no less awe-inspiring for being scientific. What makes this question particularly fascinating is that it sits at the intersection of physics, philosophy, and something deeper still. When we ask how the universe began, we're really asking about the nature of causality itself. We're probing the relationship between existence and non-existence, between possibility and reality. We're trying to understand not just what happened, but how anything can happen at all. There's something peaceful about sitting with this mystery, don't you think? Not needing to solve it completely, but simply letting it wash over you like a gentle tide. The universe began somehow, and that somehow included you. Every atom in your body, every thought in your mind, every breath you take is part of that original story. You are made of universe stuff, shaped by universe forces, living on a universe stage that somehow, miraculously, came into being from absolutely nothing at all. So, as we continue our journey tonight, let's hold this question gently. Not as a problem to be solved in the next few minutes, but as a wonder to be appreciated, a mystery that connects us to the deepest workings of reality itself. Because in trying to understand how the universe began, we're really trying to understand our own place in the grand cosmic story. And what a story it is! From nothing to everything, from silence to symphony, from emptiness to the rich, complex, beautiful universe we call home. Let's see where this ancient tale takes us next. Now, here's something wonderful about this mystery. Scientists haven't just thrown up their hands and given up. Instead, they've come up with some remarkably creative theories about how it all might have started. Scientists, it turns out, are remarkably creative when faced with the impossible. When confronted with the question of how everything came from nothing, they haven't simply scratched their heads and wandered off for tea. Instead, they've proposed some of the most beautiful, bizarre, and mind-bending theories in the history of human thought. It's like a cosmic choose-your-own-adventure book, where each page offers a different way the universe might have begun. Let's start with Stephen Hawking's elegant solution, which he called the no-boundary proposal. Hawking suggested that perhaps there was no before at all. Time and space, he argued, are properties of the universe itself, so the beginning of the universe was also the beginning of time. Asking what came before the Big Bang, in this view, is like asking what's north of the North Pole. It's not that the question is wrong, exactly, it's just that it doesn't apply. There's no north of the North Pole because north stops having meaning at that point. Similarly, there's no before the beginning of time because before stops having meaning there. It's a beautifully simple idea that sidesteps the whole causality problem entirely. If time itself began with the universe, then we don't need to worry about what caused the Big Bang, because there was no time for causes to exist in. The universe simply is, in the same way that the North Pole simply is the northernmost point on Earth. But not everyone finds this solution satisfying. Some physicists prefer theories that embed our Big Bang in something larger, more ongoing. Enter the idea of eternal inflation and the multiverse. This theory suggests that what we call the Big Bang wasn't really the beginning of everything, just the beginning of our particular corner of existence. Picture a vast, eternally expanding cosmic foam where new bubble universes are constantly forming. Our universe is just one of these bubbles, created when a tiny region of space underwent rapid, exponential inflation. In this view, our Big Bang was just one inflationary event in a much larger, eternally inflating cosmos. Somewhere out there, other universes are bubbling into existence, each with their own physics, their own laws, their own stories. It's like a cosmic bakery where universe bread is constantly rising, each loaf unique but baked in the same cosmic oven. We happen to live in one particular loaf, but there are countless others we'll never see or interact with. Then there's the Big Bounce theory, which takes a completely different approach. What if our universe isn't the first universe, but just the latest in an infinite series? This cyclical model suggests that universes expand and contract in an eternal rhythm, like a cosmic heartbeat. Our current universe grew from the collapse of a previous one, and someday, billions of years from now, it will collapse again, only to bounce back and create yet another universe. It's an oddly comforting idea, this notion of cosmic recycling. Instead of a single, dramatic beginning, you have an endless cycle of growth and contraction, expansion and collapse. The universe becomes less like a one-time explosion and more like breathing, endlessly inhaling and exhaling across cosmic timescales. Physicist Roger Penrose has proposed his own twist on the cyclical idea, called conformal cyclic cosmology. Penrose suggests that at the extremes of infinitely big and infinitely small, the universe loses its sense of scale entirely. The end of one universe, when everything has spread out and cooled down to nearly nothing, becomes mathematically identical to the beginning of the next universe. When everything was compressed into an infinitely small point, it's as if the universe has a way of forgetting its own size, allowing the end of one cosmic chapter to seamlessly become the beginning of the next. And then there's string theory, which offers perhaps the most exotic origin story of all. String theory describes reality as composed of tiny vibrating strings in an 11-dimensional hyperspace. Most of these dimensions are curled up so small we can't detect them, but they're there, humming away at frequencies far too small for us to hear. In this framework, our three-dimensional universe might be what's called a brane, a sort of cosmic membrane floating in higher dimensional space. The Big Bang, in this view, could have resulted from the collision of two such branes. Imagine two cosmic soap bubbles bumping into each other in a space we can't even properly visualize. When they collide, the energy released creates a new universe, complete with space, time, matter, and the physical laws we observe. It's like cosmic billiards played in dimensions we can barely imagine, where the click of the collision echoes as the birth of everything we know. Each of these theories offers a different lens through which to view the ultimate mystery. Some emphasize the uniqueness of our cosmic moment, others embed it in larger, ongoing processes. Some see the beginning as truly fundamental, others as just another event in an endless cosmic story. And here's the beautiful thing, we don't have to choose just one. Right now, the origin of the universe remains a choose-your-own adventure, where all the adventures are still possible. Perhaps Hawking was right, and time simply began when the universe did. Perhaps we're living in one bubble of an eternally inflating multiverse. Perhaps we're part of an endless cosmic cycle or the result of colliding dimensions we can't even see. The truth is, we don't know yet. And there's something wonderfully humbling about that uncertainty. For now, the origin remains an unfolding mystery, a question that connects us to the deepest workings of reality while reminding us how much we still have to discover. Each theory offers its own poetry, its own vision of how something can emerge from nothing, how existence can spark into being from the deepest possible silence. But regardless of which theory ultimately proves correct, they all agree on one remarkable fact. Somehow, the universe began in a state of almost unimaginable heat and density. If you think your oven gets hot, wait until you hear about the Large Hadron Collider. Deep beneath the border between France and Switzerland, scientists have created temperatures that would make the sun jealous. We're talking about 5.5 trillion degrees Celsius, hot enough to make atoms dance apart, hot enough to recreate conditions that existed just moments after the Big Bang. And yet, as impossibly hot as that sounds, it's nothing compared to what the universe experienced in its very first instance. To understand just how extraordinary those early moments were, let's take a gentle wander through the landscape of heat itself. We're used to thinking about temperature in everyday terms: the warmth of summer sunshine, the chill of winter air, the satisfying heat of a cup of tea. But temperature, at its heart, is really about motion. Heat is just atoms and molecules jiggling around. The faster they jiggle, the hotter things get. At room temperature, the molecules in the air around you are zipping about at roughly the speed of a bullet. When you heat something up, you're essentially telling those molecules to move faster, to dance with more energy. Heat water enough, and the molecules dance so enthusiastically that they break free from each other entirely, becoming steam. Cool them down, and they slow their dance until they lock together as ice. But there are limits to how hot things can get, just as there are limits to how cold they can become. You've probably heard of absolute zero, the coldest possible temperature where all molecular motion stops entirely. It's minus 273.15 degrees Celsius, a temperature so cold that atoms barely whisper to each other. But did you know there's also an absolute hot? A temperature so extreme that the very concept of heat starts to break down? This ultimate temperature is called the Planck temperature, and it clocks in at roughly 1.4 times 10 to the 32nd power Kelvin. That's a number so large it's almost meaningless to write out in full, a 1 followed by 32 zeros. To put this in perspective, if the heat inside the sun's core is like a candle flame, then the Planck temperature is like every star in the observable universe burning at once, concentrated into a space smaller than an atom. At the Planck temperature, something fascinating and terrible happens. The energy becomes so intense that it literally tears particles apart with its own gravitational field. The distinction between matter and energy becomes meaningless. Space and time themselves begin to fluctuate like ocean waves in a storm. It's not just hot in any sense we understand, it's a temperature that breaks the very framework we use to think about temperature. And here's the remarkable thing. The universe, in its very first instant, may have been exactly this hot. During the Planck era, that first fleeting moment from time 0 to 10 to the minus 43 seconds after the Big Bang, the entire cosmos was compressed into a space unimaginably smaller than a proton, and it was burning at the Planck temperature. It wasn't just the hottest thing that ever existed, it was the hottest thing that could ever exist. Imagine, if you can, all the energy that would eventually become every star, every planet, every galaxy, every particle of matter, and every photon of light, all crushed together into a space so small it defies description. The density was infinite, or close enough to infinite that our mathematics simply give up and start returning error messages. The temperature was so extreme that the four fundamental forces of nature, the forces that govern everything from the fall of an apple to the formation of galaxies, were unified into a single, unimaginably powerful force. This is what physicists sometimes call the grand unified theory era, when there was no distinction between the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. They were all one force, the way white light contains all colors but appears as a single brightness. As the universe expanded and cooled, this unified force began to split apart, like white light passing through a prism and separating into a rainbow. But during that first instant, when everything was unified and impossibly hot, the normal rules of physics didn't apply. General relativity, Einstein's beautiful theory of gravity and space-time, becomes incompatible with quantum mechanics, our equally beautiful theory of the very small. It's like trying to use two different languages to describe the same conversation, languages that don't quite translate into each other. This is why those first moments remain so mysterious. We have two excellent theories that work wonderfully in their own domains, but when we try to combine them to understand the universe at the Planck temperature, they start arguing with each other like tired siblings on a long car journey. The mathematics becomes unstable, the predictions become infinite, and physicists start reaching for very strong coffee. And yet, something happened during that inconceivable moment. Somehow, from that state of infinite density and impossible heat, the universe began its journey toward the cool, structured cosmos we see today. The expansion that began in that first instant is still continuing now, 13.8 billion years later. Every breath you take exists because of processes that began when the universe was hotter than anything we can properly imagine. It's humbling to think that everything we know and love, every gentle moment and every quiet evening, emerged from conditions so extreme they challenge the very foundations of physics. The warmth of sunlight on your face, the comfortable temperature of your room, the heat that keeps your heart beating, all of it traces back to that first moment when the universe was not just hot, but impossibly, fundamentally, magnificently hot. In a way, we're all children of that cosmic furnace, cooled and calmed by billions of years of expansion, but still carrying the memory of that original fire in every atom of our being. Let's see what happened as that impossible heat began to cool, and the universe took its first tentative steps toward becoming the place we call home. Picture a time when the entire observable universe could fit in a space smaller than a single atom. Not just smaller than an atom, but smaller than anything we have names for. We're talking about the Planck length, a distance so tiny that if you enlarged an atom to the size of our solar system, the Planck length would still be smaller than a grain of sand. And in this impossibly small space, for an impossibly brief moment, all of existence was squeezed together in a state so extreme, it makes our best physics theories throw up their hands in defeat. This was the Planck era, lasting from the very beginning of time until 10 to the minus 43 seconds after the Big Bang. To put that time span in perspective, imagine a single second. Now divide it by 10, then divide that by 10, then keep dividing by 10 41 more times. That's how long the Planck era lasted. It's such a brief moment that light, traveling at its famously breakneck speed, could only cross a distance smaller than a proton. And yet, in this fleeting instant, everything we see in the universe today was already present, just compressed beyond all imagination. During the Planck era, something remarkable happened. All four fundamental forces of nature were unified. Think of it as the universe's brief moment of perfect harmony. The strong nuclear force, which holds atomic nuclei together. The weak nuclear force, which governs certain types of radioactive decay. The electromagnetic force, which powers everything from lightning to the gentle pressure of sunlight. And gravity, which keeps your feet on the ground and planets in their orbits. For that single, precious moment, they were all one force, working together in perfect cosmic symphony. It's a bit like imagining a master musician playing 4 instruments simultaneously, creating a sound so complex and beautiful that our ears can only hear it as one pure note. As the universe expanded and cooled, this unified force began to separate, like that pure note breaking apart into distinct harmonies. First, gravity split off, becoming the gentle but relentless force we know today. Later, the other forces would separate too, each taking on their own personality, their own role in the cosmic story. But here's where things get beautifully strange. At the scales of the Planck era, our 2 greatest theories of physics, general relativity and quantum mechanics, become incompatible. It's not that one is wrong and the other is right. They're both extraordinarily successful in their own domains. General relativity describes gravity and the large-scale structure of spacetime with elegant precision. Quantum mechanics explains the behavior of atoms and particles with remarkable accuracy. But when you try to use both theories simultaneously to describe the Planck era, they disagree so fundamentally that the mathematics breaks down entirely. This isn't just a technical problem. It's a sign that we're missing something profound about the nature of reality itself. It's like having 2 excellent maps of the same territory that somehow show completely different landscapes. Both maps work perfectly for their intended purposes, but when you try to overlay them, nothing lines up. The legendary physicist John Archibald Wheeler, who had a gift for finding poetry in mathematics, described this era using a term that captures its essence perfectly: quantum foam. During the Planck era, Wheeler suggested, space-time itself wasn't smooth and predictable, but was instead bubbling and churning like foam on an ocean wave. At these incredible scales, the very fabric of space and time becomes dynamic and chaotic, with tiny black holes and wormholes popping in and out of existence faster than you can blink. Imagine looking at the surface of the ocean from an airplane. From that height, the water looks smooth and blue, a gentle, continuous surface. But if you could zoom in impossibly close, down to the molecular level, you'd see a completely different picture: molecules bouncing and colliding, binding and separating, a constant dance of motion and change. Wheeler's quantum foam suggests that space-time at the Planck scale is similarly active, with the very structure of reality fluctuating and shifting in ways we can barely imagine. In this quantum foam, the normal rules don't apply. Cause and effect become fuzzy concepts. Particles can pop into existence from nothing and disappear just as quickly. The distinction between space and time becomes blurred. It's not chaos exactly, but it's not order in any sense we recognize either. It's like watching the universe learn how to exist, experimenting with different ways of being before settling into the more stable patterns we observe today. This era represents the ultimate frontier of physics, the place where our understanding bumps up against the deepest mysteries of existence. We can describe it mathematically, we can theorize about what might have happened, but we can't quite grasp it with the same confidence we have about later periods in cosmic history. It's simultaneously the most important era in the universe's story and the most inaccessible to our current understanding. And yet, everything emerged from this moment. Every star you've ever wished upon, every sunset you've ever watched, every breath you've ever taken can trace its ancestry back to this period of cosmic chaos and creativity. In a sense, the Planck era wasn't just the beginning of the universe, it was the beginning of the possibility of everything that would come after: atoms and molecules, planets and stars, life and consciousness, love and dreams, and quiet evenings listening to stories about the cosmos. There's something wonderfully humbling about the Planck era. It reminds us that the universe began not with order and predictability, but with mystery and strangeness so profound that our best theories can only point toward it like signposts, indicating a destination they can't quite reach. It suggests that mystery isn't a bug in our understanding of the universe, but a feature, a reminder that reality is far stranger and more wonderful than we might ever fully comprehend. As we continue our journey through cosmic history, we'll see how this initial chaos gradually gave way to the structured universe we know today. But it all began here, in this moment of pure potential, when physics itself was still learning the rules of the game. In the universe's earliest moments, all the forces were best friends, but gravity was the first to leave the party. Picture the end of the Planck era, when the universe had grown from inconceivably tiny to merely unimaginably small, and the temperature had dropped from infinite to merely trillion upon trillions of degrees. In this slightly more civilized cosmic environment, something remarkable happened. Gravity decided it needed some space. Until this moment, all four fundamental forces had been unified in perfect harmony, like a cosmic quartet singing the same note. But as the universe expanded and cooled, this unity began to break down. Gravity, that gentle but persistent force that would eventually shape galaxies and keep your feet on the ground, was the first to step away from the group and establish its own identity. This separation wasn't dramatic or violent. There were no cosmic fireworks or universal thunderclaps. Instead, it was more like watching a single voice emerge from a choir, gradually becoming distinct while still harmonizing with the whole. Gravity simply began to behave differently from the other forces, developing its own personality and its own way of interacting with the universe. What remained after gravity's departure was still quite impressive. A unified strong force that combined what we now know as the strong nuclear force, the weak nuclear force, and the electromagnetic force. Think of it as a cosmic Swiss Army knife, one tool that could handle 3 different jobs. This electro-strong force was incredibly powerful, far more intense than any of the forces we observe in today's universe. The era that followed gravity's separation is called the Grand Unification Epoch, and it was a time of extraordinary cosmic creativity. With gravity now operating independently, but the other 3 forces still working together, the universe became a kind of particle physics playground. Energy levels were so high that matter and antimatter could pop into existence spontaneously, only to annihilate each other moments later in brilliant flashes of pure energy. It was during this era that the universe began to develop its first hint of structure, though not anything we'd recognize as orderly. Instead, it was more like cosmic jazz improvisation, with particles appearing and disappearing, transforming into each other, dancing to rhythms we can barely comprehend. Quarks transformed into electrons. Electrons became photons. Photons split into pairs of particles and antiparticles. Everything was in constant flux, a free-for-all of energy and matter, where the only constant was change itself. Imagine a cosmic soup where the ingredients keep transforming. One moment you have what might become a proton, the next it's become a shower of light particles, then suddenly it's something else entirely. The laws of conservation still applied, so energy couldn't be created or destroyed, but it could take on any form it pleased. It was like having a magical kitchen where flour could spontaneously become eggs, eggs could become butter, and butter could become cake, all while maintaining the same total amount of ingredients. The temperature during this epoch was still almost incomprehensibly hot, though significantly cooler than during the Planck era. We're talking about 10 to the 27th degrees, hot enough that ordinary matter as we know it simply couldn't exist. Atoms were impossible. Even atomic nuclei were far too complex for this energetic environment. Only the most fundamental particles could survive, and even they existed in a constant state of transformation. But gravity, now operating on its own, was already beginning to make its influence felt. Though it's the weakest of the four fundamental forces, gravity has a special property. It always attracts, never repels. While the other forces can push and pull in equal measure, gravity only knows how to bring things together. Even in this era of cosmic chaos, gravity was quietly working to create the first hints of structure in the universe. It's worth pausing to appreciate just how strange this epoch was. In our everyday experience, the fundamental forces are dramatically different from each other. Gravity holds you in your chair and keeps planets orbiting stars. The electromagnetic force powers your phone and creates the northern lights. The strong nuclear force holds atomic nuclei together against the electromagnetic repulsion of protons. The weak nuclear force governs certain types of radioactive decay. They seem like completely different phenomena, each with its own personality and role to play. But during the grand unification epoch, three of these forces were essentially the same thing, just different aspects of a single, more fundamental interaction. It's like discovering that three actors who play very different characters in a movie are actually the same person in elaborate costumes. The universe, in its earliest moments, was far more unified than it appears today. This unity also meant that the distinction between different types of particles was far less clear than it is now. The categories we use today, like matter particles and force particles, hadn't fully established themselves yet. Everything was more fluid, more interconnected, more willing to transform into something else at a moment's notice. As the universe continued to expand and cool, this cosmic free-for-all gradually began to settle down. The endless transformations became less frequent, the wild fluctuations began to stabilize, and the stage was set for the next major transition in cosmic history. But for this brief, shining moment, the universe was a place of almost pure potential, where anything could become anything else, and the only limit was the imagination of physics itself. Looking back on this era, it's remarkable to think that all the structure and complexity we see in today's universe, from atoms to galaxies to conscious beings pondering the cosmos, emerged from this period of apparent chaos. The grand unification epoch wasn't just a time of cosmic confusion, it was a time of cosmic creativity. When the universe was establishing the fundamental rules and relationships that would govern everything that came after. Soon, even this relative simplicity would give way to greater complexity as the electro-strong force itself began to show signs of strain. Sometimes the best theories have the most embarrassing problems. By the 1970s, the Big Bang theory was looking pretty impressive. It explained why the universe was expanding, predicted the cosmic microwave background radiation, and accurately described the abundance of light elements like hydrogen and helium. But like a beautiful symphony with a few notes that just didn't sound quite right, the standard Big Bang model had some puzzling issues that kept cosmologists awake at night. These weren't small problems that could be fixed with a bit of theoretical duct tape. They were fundamental mysteries that struck at the heart of how we understood the universe's early moments. And the more scientists looked at them, the more they realized that something important was missing from their cosmic story. The first problem was called the horizon problem, and it had to do with temperature. When scientists looked out into space with their most sensitive instruments, measuring the temperature of the cosmic microwave background radiation, they discovered something remarkable and troubling. No matter which direction they pointed their telescopes, the temperature was almost exactly the same, varying by only tiny fractions of a degree. Now, this might not sound like a problem at first. Uniformity seems like a good thing, right? The trouble was that these regions of space were so far apart that light hadn't had enough time to travel between them since the Big Bang. According to the Standard Model, these distant regions had never been in contact with each other. They were like two people in separate rooms who had never met, never communicated, and never influenced each other, yet somehow they were wearing exactly the same outfit. Think about it this way. Imagine you're making soup, but you're not allowed to stir it. You pour hot broth into one side of the pot and cold broth into the other side. Then you walk away for a few minutes. When you come back, you'd expect to find hot soup on one side and cold soup on the other. You certainly wouldn't expect to find that the entire pot had somehow reached exactly the same temperature without any mixing. Yet that's essentially what the universe appeared to have done on a cosmic scale. For regions of space to have the same temperature, they need to have been in thermal equilibrium at some point, meaning they need to have exchanged energy and information. But, according to the standard Big Bang timeline, vast swaths of the observable universe had never been close enough together to communicate, even at the speed of light. It was as if the universe had conspired to be uniform without any apparent mechanism for achieving that uniformity. The second major problem was called the flatness problem, and it dealt with the geometry of space itself. Einstein's general relativity tells us that space can be curved, like the surface of a sphere or a saddle. The amount of curvature depends on how much matter and energy the universe contains. If there's too much, space curves inward and the universe eventually collapses. If there's too little, space curves outward and the universe expands forever, growing cold and empty. But if the amount is just right, space is perfectly flat, like an infinite sheet of paper. When cosmologists measured the geometry of our universe, they found it to be remarkably close to perfectly flat. This was a problem because flatness, in cosmic terms, is an incredibly unstable condition. It's like balancing a pencil on its point. Even the tiniest deviation from perfect balance and the pencil falls over. Similarly, even the smallest deviation from the critical density needed for flatness and the universe either collapses quickly or expands so rapidly that galaxies never form. For our universe to be as flat as it appears today, the density in the early universe would have had to be fine-tuned to an extraordinary degree. We're talking about precision to 1 part in 10 to the 60th power, a number so specific it's like hitting a target the size of a single atom from a distance of several billion light-years. It seemed like an impossible coincidence. The third problem was more exotic, but equally puzzling: the magnetic monopole problem. Certain theories about the early universe predicted that it should have produced vast quantities of magnetic monopoles, particles that would be like tiny bar magnets with only a north pole or only a south pole. These theoretical particles would be incredibly massive and stable, and if they had been created in the early universe, they should still be around today in enormous numbers. The problem was that nobody had ever found one. Not a single magnetic monopole had been detected despite decades of searching. It was as if the theories predicted that the early universe should have been manufacturing cosmic elephants by the trillion, but when scientists looked around, they couldn't find even one elephant dropping. These three problems, the horizon problem, the flatness problem, and the magnetic monopole problem, represented serious challenges to the standard Big Bang model. They weren't just minor theoretical glitches. They suggested that something fundamental was missing from our understanding of the universe's earliest moments. Scientists tried various solutions, but none seemed to address all three problems simultaneously. It was like trying to fix a car that had 3 different mechanical issues, each requiring a different type of repair. You could fix the engine, but then the brakes wouldn't work. Fix the brakes, and the transmission would fail. There seemed to be no single solution that could address all the problems at once. But in science, problems often point the way toward breakthroughs. These puzzles weren't signs that the Big Bang theory was wrong, they were clues that it was incomplete. Somewhere in the universe's early history, something had happened that wasn't accounted for in the standard model. Something that could solve all three problems with one elegant solution. What was needed was a new chapter in the cosmic story, an event or process that could explain why the universe was so uniform, so flat, and so mysteriously free of magnetic monopoles. And in the early 1980s, a young physicist named Alan Guth proposed exactly that, a period of rapid exponential expansion that would come to be known as cosmic inflation. What if the universe had the most dramatic growth spurt in history? In 1980, a young physicist named Alan Guth was wrestling with those troublesome problems we just discussed when he had what he later called the most exciting moment of his career. Working late into the night, scribbling equations and drinking what was probably far too much coffee, he stumbled upon an idea so elegant and powerful that it would revolutionize our understanding of the cosmos. Guth proposed that in the universe's earliest moments, between about 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, something extraordinary happened. The universe underwent a period of exponential expansion so rapid and dramatic that it makes every other example of fast growth seem positively leisurely by comparison. He called this period cosmic inflation, and it's like nothing we experience in everyday life. To understand just how extreme this expansion was, imagine a region of space smaller than a proton, containing perhaps a few dozen particles. Now, imagine that in less time than it takes light to cross that tiny space, this region expands to become larger than a grapefruit. That's not just fast growth, that's physics, defying mind, bending, reality, reshaping expansion that doubled the size of space itself roughly 90 times in a fraction of a second. But even that description doesn't capture the full strangeness of what happened. Let's try another way to picture it. If you took a single atom and inflated it at the same rate the universe expanded during inflation, that atom would grow larger than our solar system in the blink of an eye. Its expansion so rapid that if you could somehow watch it happen, you wouldn't see gradual growth, but rather an instantaneous leap from inconceivably tiny to merely unimaginably large. During inflation, space wasn't just getting bigger, it was being created from nothing. New space was coming into existence faster than light could travel across it. This might sound like it violates Einstein's rule that nothing can travel faster than light, but there's a crucial distinction. It wasn't matter or energy moving through space faster than light, it was space itself expanding. Einstein's speed limit applies to things moving through space, not to space itself stretching. It's a bit like standing on an airport moving walkway that's accelerating. You're not walking faster than your normal pace, but the walkway beneath your feet is carrying you along at increasing speed. Similarly, during inflation, particles weren't moving faster than light through space. Space itself was carrying them along as it expanded at an incredible rate. Two particles that started next to each other could find themselves separated by vast distances without either one actually moving. This period of inflation was driven by something physicists call an inflaton field, though different theories propose different mechanisms. The basic idea is remarkably strange, a form of energy that filled all of space and had a very unusual property. Instead of diluting as space expanded, the way normal matter and energy do, it maintained a constant density. As space grew, more inflaton field energy appeared to fill the new volume. Think of it like a magical honey jar that never empties. No matter how much honey you pour out, the jar remains full. In inflation, no matter how much space expanded, the energy density of the inflaton field remained the same, constantly generating new energy to fill the new space. This created a kind of cosmic feedback loop. The inflaton field caused space to expand, which created more inflaton field energy, which caused even more expansion, and so on. There are actually several different flavors of inflation theory, each with its own personality. Slow-roll inflation suggests the inflaton field was like a ball rolling very slowly down a gently sloped hill, taking its time to reach the bottom. Chaotic inflation proposes that inflation happened randomly in different regions, creating a patchwork of inflating bubbles. Eternal inflation suggests that once inflation starts, it never really stops. It just creates new regions of space that then inflate on their own, leading to an endless cascade of universe bubbles. The eternal inflation scenario is particularly mind-bending. If it's correct, our entire observable universe, containing hundreds of billions of galaxies, is just one tiny bubble in an infinite cosmic foam of other inflating regions. Somewhere out there, unimaginably far away, other bubbles might contain universes with completely different physics, different particles, different forces. It's the ultimate multiverse, where anything that can happen does happen, somewhere. Now, here's where inflation becomes not just fascinating, but elegantly useful. It solved all three of those troublesome problems in one stroke. The horizon problem, the puzzle of why distant regions of the universe have the same temperature, was resolved beautifully. Before inflation, these regions that appear unconnected today were actually close neighbors in the tiny pre-inflation universe. They had plenty of time to reach thermal equilibrium when they were all squeezed together in a space smaller than an atom. Inflation then stretched them apart so rapidly that they ended up on opposite sides of the observable universe, but they retained their shared temperature from their intimate early relationship. The flatness problem was solved just as elegantly. Any initial curvature in the universe would have been stretched out by the exponential expansion of inflation, just like the way the surface of a balloon appears flatter and flatter as you blow it up. If you inflate a balloon enough, any small patch of its surface becomes so flat that it appears perfectly straight. Similarly, inflation stretched the fabric of space so much that any original curvature was smoothed out, leaving us with the remarkably flat universe we observe today. And the magnetic monopole problem? Inflation solved that too. If magnetic monopoles had been created before inflation, they would have been diluted to near invisibility by the exponential expansion. Imagine spreading a handful of marbles across a surface the size of a penny, then suddenly expanding that surface to the size of a planet. The marbles would still be there, but you'd be extremely unlikely to find one in any particular location. Inflation spread out any pre-existing monopoles so much that they became essentially undetectable. But inflation did more than just solve problems. It made a remarkable prediction that we can actually test. The process of inflation, while incredibly smooth overall, wasn't perfectly uniform. According to quantum mechanics, nothing can be perfectly smooth at the smallest scales. Even the inflaton field experienced tiny quantum fluctuations, microscopic variations in its energy density. During the exponential expansion of inflation, these quantum fluctuations were stretched from subatomic scales to cosmic proportions. Imagine drawing a tiny wrinkle on a deflated balloon with the finest pen you can find, then inflating the balloon until it's the size of a house. That microscopic wrinkle would become a large, visible pattern on the balloon's surface. Similarly, quantum fluctuations that began smaller than the smallest subatomic particles were inflated until they became variations in the distribution of matter and energy across the entire observable universe. These density variations became the seeds of all the structure we see today. Regions that were slightly denser than average would attract matter through gravity, eventually becoming galaxies, stars, and planets. Regions that were slightly less dense would become the cosmic voids that separate galactic clusters. This prediction is extraordinary because it connects the smallest possible scales in physics, quantum fluctuations, with the largest structures in the universe, galaxy clusters spanning hundreds of millions of light-years. It suggests that the quantum fuzziness of the universe's earliest moments, amplified by inflation, became the cosmic architecture that shapes everything from the largest galaxy clusters to the very planet you're sitting on. And here's the beautiful part. We can actually observe these ancient quantum fluctuations today. They show up as tiny temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang. When scientists map these temperature variations with exquisite precision, they find exactly the pattern that inflation theory predicts. It's like finding the universe's baby pictures and discovering that they match perfectly with the family photos from later life. Inflation theory wasn't just an elegant solution to existing problems. It transformed our understanding of how the universe works at its most fundamental level. It suggests that our entire observable cosmos, with all its complexity and beauty, emerged from quantum fluctuations in a field of energy that existed for less than a trillionth of a trillionth of a trillionth of a second. You are, quite literally, made possible by quantum uncertainty, magnified to cosmic proportions by the most dramatic expansion in the history of existence. Let's take a gentle step forward now and see what happened when this period of incredible expansion finally came to an end, and the universe began the next chapter of its remarkable story. As the universe cooled down, it started breaking its own rules. After the dramatic expansion of inflation had stretched space and diluted the cosmic energy, the universe found itself in a very different situation. It was now vast, relatively cool, and ready for the next phase of its story. The era of cosmic inflation was over, but the era of cosmic evolution was just beginning. And like a master conductor preparing an orchestra, the universe began to organize its forces into the distinct voices we recognize today. Remember that during the grand unification epoch, 3 of the 4 fundamental forces were still unified in the electro-strong force, while gravity had already established its independence. But as the temperature continued to drop, this remaining unity became unstable. The universe was cooling like a cosmic cup of tea, and just as cooling tea eventually reaches a point where it can no longer dissolve as much sugar, the cooling universe reached a point where it could no longer maintain the unification of its forces. This process is called symmetry breaking, and it's one of the most beautiful concepts in physics. The early universe was characterized by perfect symmetry, where forces and particles were indistinguishable from each other, like identical dancers performing the same choreography. But symmetry, while elegant, can also be unstable. Sometimes the most balanced state is not the most stable state, and given enough time, even perfect symmetry will find a way to break. Think about a pencil balanced perfectly on its point. That's a highly symmetrical state, but it's also incredibly unstable. The slightest vibration, the tiniest breath of air, and the pencil will fall in some random direction. Once it falls, the symmetry is broken. The pencil now has a preferred direction, a definite orientation in space. Similarly, as the universe cooled, its perfect symmetry became unstable and began to break, giving the forces distinct identities and behaviors. The first major symmetry breaking after gravity's departure was the split between the strong nuclear force and the electro-weak force. This happened when the universe was about 10 to the minus 11 seconds old and had cooled to a temperature of about 10 to the 15th degrees Kelvin. It might still sound impossibly hot, but compared to the Planck temperature, it was practically frigid. When this symmetry broke, the strong nuclear force emerged with its own unique personality. This is the force that holds atomic nuclei together, binding protons and neutrons into stable clusters despite the electromagnetic repulsion between positively charged protons. It's incredibly powerful but has a very short range, only operating over distances comparable to the size of an atomic nucleus. Outside that tiny range, the strong force simply doesn't care what happens. The strong force is also responsible for something that seems almost magical. Most of the mass of ordinary matter doesn't come from the particles themselves, but from the binding energy that holds them together. When quarks are bound together by the strong force to form protons and neutrons, the energy of that binding, according to Einstein's famous equation E equals mc squared, contributes to the mass of the resulting particle. In fact, more than 90% of your body's mass comes not from the quarks themselves, but from the energy that binds them together. Meanwhile, the electroweak force, though it would later split into the electromagnetic and weak nuclear forces, remained unified for a while longer. This combined force governed interactions involving photons, the particles of light, as well as the interactions responsible for certain types of radioactive decay. The electroweak force was democracy in action. Electrons, photons, and other particles were all treated equally, able to transform into each other with relative ease. During this period, called the electroweak epoch, the universe was a very different place from today. It was still far too hot for atoms to exist, or even for atomic nuclei to remain stable. Instead, it was filled with a hot plasma of fundamental particles, quarks, electrons, photons, and neutrinos, all interacting in a complex dance of creation and annihilation. But even though individual particles couldn't form stable structures yet, the universe was beginning to develop the rules that would govern all future interactions. The strengths of the forces, their ranges, and their preferred ways of interacting were all being established during this epoch. It was like the universe was writing its own constitution, setting down the fundamental laws that would govern everything from the formation of atoms to the eventual emergence of galaxies. The process of symmetry breaking also introduced something new into the universe, the concept of different types of particles with different properties. Before symmetry breaking, particles were more like different aspects of the same underlying entity. After symmetry breaking, they became genuinely distinct, each with its own mass, charge, and behavior patterns. This is similar to what happens when water freezes into ice. Liquid water has a high degree of symmetry, it looks the same from any direction, and its molecules are free to move and rotate. But when it freezes, that symmetry is broken. Ice crystals have preferred directions and orientations. The water molecules lock into specific patterns, and the resulting ice has properties very different from the original liquid. As the universe continued to expand and cool, it was preparing for the next major symmetry breaking event, one that would split the electroweak force and introduce the concept of mass itself. But for now, in this electroweak epoch, the cosmos was finding its rhythm, establishing the basic rules that would govern matter and energy for the rest of cosmic history. The universe was becoming less unified but more interesting, less symmetrical but more structured. It was learning to be complex, preparing for the emergence of the rich, diverse cosmos we see today. Each symmetry-breaking event was like the universe choosing a path at a cosmic crossroads, committing to a specific way of organizing matter and energy that would shape everything that followed. Soon, the next great transition would arrive, introducing one of the most mysterious and important concepts in all of physics, the origin of mass itself. Mass, believe it or not, was not always a given. In the very early universe, particles zipped around at the speed of light, weightless and carefree as photons. The concept of mass, that fundamental property that gives things heft and substance, hadn't been invented yet. It took a special kind of cosmic magic to change that, and that magic has a name: the Higgs field. As the universe continued to cool after the separation of the strong force, it approached another critical moment of symmetry breaking. This time, it wasn't just about forces splitting apart. It was about fundamentally changing what it means to be a particle with mass. We're talking about the moment when the electroweak force finally broke into the electromagnetic force and the weak nuclear force, and in doing so, introduced the very concept of mass to the universe. The story begins with a field, an invisible presence that fills every cubic inch of space throughout the entire cosmos. This is the Higgs field, named after physicist Peter Higgs, who, along with several colleagues, proposed its existence in the 1960s. Unlike other fields we're familiar with, like magnetic fields or gravitational fields, the Higgs field has a peculiar property. It has a non-zero value even in its lowest energy state. In other words, even when nothing is happening, the Higgs field is still there, humming quietly in the background like cosmic elevator music. Think of it like an invisible ocean that fills all of space. Now, imagine different particles swimming through this ocean, and depending on how much they interact with the water, they experience different amounts of resistance. Some particles, like photons, glide through the Higgs ocean without any interaction at all, like frictionless swimmers who barely disturb the water. These particles remain massless, always traveling at the speed of light. But other particles interact with the Higgs field quite strongly. They're like swimmers wearing heavy winter coats, pushing through thick honey instead of water. The more a particle interacts with the Higgs field, the more resistance it experiences, and this resistance is what we call mass. Electrons interact with the field a little bit, so they have a small mass. Protons and neutrons interact more strongly, so they're heavier. The top quark interacts very strongly indeed, making it one of the most massive fundamental particles we know. It's a beautifully simple idea. Mass isn't an intrinsic property of particles themselves, but rather a measure of how much they interact with this invisible field that permeates all of space. Before the Higgs field turned on, all particles were massless and traveled at the speed of light. After the field activated, particles that interacted with it gained mass and had to slow down to speeds less than that of light. This moment when the Higgs field activated was another symmetry-breaking event, but perhaps the most consequential one in cosmic history. It happened when the universe was about 1/trillionth of a second old and had cooled to a temperature of about 1,000 billion degrees Kelvin. Still unimaginably hot, but cool enough for this crucial transition to occur. When the Higgs field turned on, it was like the universe suddenly developed friction. Particles that had been zipping around at light speed suddenly found themselves slowing down, acquiring mass, and behaving in entirely new ways. The electromagnetic force separated from the weak nuclear force, each taking on its own distinct personality. The electromagnetic force became the force we know today, responsible for light, electricity, magnetism, and the chemical bonds that hold molecules together. The weak nuclear force became responsible for certain types of radioactive decay and plays a crucial role in how stars burn their nuclear fuel. But the Higgs field did more than just give particles mass. It fundamentally changed the character of the universe. With mass came the possibility of more complex structures. Massless particles can only travel at the speed of light, but massive particles can slow down, change direction, and interact with each other in more intricate ways. The introduction of mass was like giving the universe a new set of tools for building complexity. The existence of the Higgs field was a theoretical prediction for almost 50 years before it was finally confirmed. Scientists at CERN, The European Particle Physics Laboratory spent decades building more and more powerful particle accelerators, trying to find evidence of the field. The challenge was that you can't observe the Higgs field directly, any more than you can see the ocean by looking at water. Instead, you have to look for the Higgs boson, a particle that represents ripples in the Higgs field itself. Finally, in 2012, scientists at the Large Hadron Collider announced that they had found it. By smashing protons together at enormous energies, they had created conditions extreme enough to produce Higgs bosons, which then decayed into other particles that could be detected. It was like proving the existence of an invisible ocean by creating waves and watching how they break on the shore. The discovery of the Higgs boson was more than just a scientific triumph. It was confirmation of our understanding of how mass works at the most fundamental level. It validated decades of theoretical work and provided the final piece of what physicists call the standard model of particle physics. Today, every time you feel the weight of an object in your hand, every time you watch something fall or feel your own body's weight against the ground, you're experiencing the effects of the Higgs field. The mass of every atom in your body, the resistance you feel when you try to accelerate your car, the fact that you can't travel at the speed of light, all of this is because particles in your body interact with an invisible field that fills all of space. The universe, having learned how to create mass, was now ready for its next great adventure, building the first complex particles and exploring the delicate balance between matter and antimatter. For a brief time, the universe was essentially a very hot, very dense particle soup. Picture the most chaotic kitchen you can imagine. Ingredients flying everywhere, everything mixing with everything else, temperatures so extreme that normal cooking rules simply don't apply. Except instead of making dinner, the universe was cooking up the fundamental building blocks of all matter. This was the quark era, and it was one of the most creative periods in cosmic history. Now that particles had acquired mass through their interaction with the Higgs field, the universe had entered a new phase of organization. It was still unimaginably hot and dense, but cool enough for some structure to begin emerging. The temperature had dropped to about 1 trillion degrees Kelvin, which might sound scorching, but compared to the Planck temperature, it was practically room temperature. For the first time since the Big Bang, conditions were becoming stable enough for the first composite particles to form. During this era, the universe was filled with what physicists poetically call a quark-gluon plasma. Think of it as a primordial soup where the main ingredients were quarks, the fundamental building blocks of protons and neutrons, and gluons, the particles that carry the strong nuclear force. These weren't organized into the neat, stable packages we call atoms yet. Instead, they existed in a state of controlled chaos, a hot, dense medium where quarks and gluons could move freely, unconfined by the usual rules that govern matter today. In our everyday world, quarks are always locked up inside larger particles like protons and neutrons. The strong force that binds them together is so powerful that individual quarks can never exist on their own under normal conditions. It's like having a group of extremely social particles that simply cannot bear to be alone. But in the quark-gluon plasma of the early universe, temperatures were so high that even these strong bonds couldn't hold, and quarks roamed free like cosmic nomads. The universe during this period was a particle physicist's dream laboratory. Every type of fundamental particle that we know exists today was present in abundance. Quarks of all 6 types, leptons like electrons and neutrinos, photons carrying light and electromagnetic energy, and all the force-carrying particles that mediate interactions between them. It was the most complete and democratic particle democracy the universe has ever known. But here's where things get really interesting. The universe was also engaged in one of the most important balancing acts in cosmic history, the delicate dance between matter and antimatter. For every particle, nature has created an antiparticle with identical mass but opposite charge. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy, leaving nothing behind but photons. In the early universe, particles and antiparticles were being created and destroyed constantly, in perfect balance. The energy was so intense that particle-antiparticle pairs could pop into existence spontaneously, exist for a brief moment, then find each other and annihilate back into energy. It was like a cosmic dance, where every dancer had a perfect partner, and when they met, they both vanished in a burst of light. This presented the universe with a fundamental problem. If matter and antimatter were created in equal amounts and annihilated each other perfectly, how did any matter survive to form the universe we see today? By all rights, everything should have annihilated into pure radiation, leaving behind a cosmos filled with nothing but light. Yet here we are, made of matter, sitting on a planet made of matter, orbiting a star made of matter, in a galaxy filled with matter. Clearly, something went wrong with the perfect balance between matter and antimatter. Or perhaps something went wonderfully right, depending on your perspective. The solution lies in a tiny but crucial asymmetry. For every billion antimatter particles that were created, the universe managed to create 1,000,000,001 matter particles. That's an imbalance of just 1 part in 1,000,000,000, barely detectable, smaller than the measurement error in most scientific experiments. But it was enough. When the Great Annihilation occurred, 1,000,000,000 matter particles met 1,000,000,000 antimatter particles and cancelled each other out in spectacular bursts of energy. But that one extra matter particle had no antimatter partner to dance with, so it survived. Across the entire universe, all those lone particles without partners became the matter that eventually formed stars, planets, and people. This cosmic asymmetry is one of the great mysteries of modern physics. We know it happened because we're here to observe it, but we don't fully understand why. Various theories suggest it might be related to subtle differences in how matter and antimatter behave under certain conditions, or perhaps to interactions with exotic particles that no longer exist. But the exact mechanism remains one of the universe's best-kept secrets. The fact that we exist at all is a testament to this tiny but crucial imbalance. Every atom in your body, every breath you take, every thought you think, exists because the universe was slightly better at making matter than antimatter. You are, quite literally, the descendant of cosmic survivors, particles that won an inconceivably vast lottery where the odds were 1,000,000,000 to 1 against. As the universe continued to expand and cool, this quark-gluon plasma began to change character. The temperature dropped to the point where quarks could no longer roam freely, and they began to cluster together, bound by the strong force into the first protons and neutrons. This transition, called confinement, marked the end of the quark era and the beginning of a new chapter in cosmic history. It's remarkable to think that all the complexity and beauty of the modern universe, from spiral galaxies to morning coffee, traces its ancestry back to this period of cosmic soup-making. The quarks that were freely swimming in that primordial plasma eventually became the building blocks of every atom in existence, including the ones that make up your body as you listen to this story. Soon, these newly confined quarks would begin the next phase of their cosmic journey, combining into the first atomic nuclei and taking the first tentative steps toward the structured matter that would eventually make stars, planets, and life itself possible. Between 10 seconds and 20 minutes after the Big Bang, the universe briefly became a cosmic kitchen. Not the chaotic, anything-goes kitchen of the quark era, but a more organized operation with specific recipes and careful timing. During this period, called Big Bang Nucleosynthesis, the universe was finally cool enough and dense enough to start cooking up the first atomic nuclei, the central cores of atoms that would eventually become the basic ingredients of everything we see today. By this point, about 10 seconds after the Big Bang, the universe had cooled to a relatively balmy billion degrees Kelvin. That's still hot enough to instantly vaporize any planet, but it was cool enough for protons and neutrons to stick together when they collided. The universe had discovered nuclear fusion, the same process that powers the sun and every other star, but on a cosmic scale. Think of the universe at this moment as a vast nuclear reactor filled with the simplest possible fuel, free protons and neutrons floating in a sea of electrons, photons, and neutrinos. The temperature was in the sweet spot where nuclear reactions could occur readily, but not so hot that the newly formed nuclei would be immediately torn apart by the intense radiation. It was like having a cosmic oven set to exactly the right temperature for nuclear baking. The first and most successful recipe was for deuterium, a heavy form of hydrogen consisting of one proton and one neutron stuck together. Deuterium formation was the crucial first step, because once you have deuterium, you can start building more complex nuclei. A deuterium nucleus could collide with another proton to form helium-3, or with another neutron to form tritium, another isotope of hydrogen. But the universe's favorite recipe was for helium-4, a nucleus containing 2 protons and 2 neutrons. This is the same helium that fills party balloons and makes your voice squeaky when you inhale it. But back then, it was being manufactured by the ton in nuclear reactions throughout the cosmos. Helium-4 is particularly stable, which made it the universe's go-to product during this era of cosmic nucleosynthesis. The nuclear kitchen operated with remarkable efficiency for those 20 crucial minutes. Starting with roughly equal numbers of protons and neutrons, the universe managed to bind about 25% of all nuclear matter into helium-4 nuclei. Another small fraction became deuterium, and tiny amounts became lithium and beryllium, but roughly 75% of the nuclear matter remained as simple hydrogen nuclei, which are just lone protons. This ratio, 75% hydrogen to 25% helium with traces of lithium, has remained remarkably constant throughout cosmic history. When astronomers look at the oldest stars in our galaxy, stars that formed from primordial gas that hadn't been processed by previous generations of stars, they find exactly this composition. It's like finding the universe's original recipe written in starlight, a cosmic cookbook that has survived for over 13 billion years. The fact that this predicted ratio matches observations so precisely is one of the strongest pieces of evidence for the Big Bang theory. It's not just that the universe is expanding or that there's cosmic microwave background radiation. It's that the universe created exactly the amounts of light elements that our theories predict it should have made during those first 20 minutes. The cosmic kitchen followed the recipe perfectly. But the nuclear cooking phase couldn't last forever. As the universe continued to expand, it also continued to cool. After about 20 minutes, the temperature had dropped below the threshold needed for nuclear fusion. The cosmic reactor shut down, not because it ran out of fuel, but because the fuel could no longer get hot enough to react. It was like turning down the oven temperature so low that your bread stops rising. There was also a curious gap in the universe's recipe book. While it was easy to make helium-4 by combining 2 protons and 2 neutrons, the next stable nucleus, carbon-12, requires 6 protons and 6 neutrons. There's no stable nucleus with 5 nuclear particles, and the one with 8 particles is extremely unstable. This meant that the universe couldn't continue cooking heavier elements during Big Bang nucleosynthesis. It had to wait for a different kind of kitchen, the cores of stars. This is why the primordial universe produced almost no elements heavier than lithium. No carbon, no oxygen, no silicon, no iron, and none of the other elements that make planets and life possible. Those would have to wait for later chapters in the cosmic story, when the first stars formed and began their own nuclear cooking programs, eventually creating and distributing the full periodic table of elements through stellar nucleosynthesis and supernova explosions. But what the universe did accomplish during those first 20 minutes was remarkable enough. Starting with nothing but free protons and neutrons, it created the nuclear basis for the two most abundant elements in the cosmos. Every hydrogen atom in every molecule of water, in every raindrop that has ever fallen, can trace its nucleus back to those first moments. Every helium atom that has ever lifted a balloon or cooled a scientific instrument was forged in the cosmic furnace of the early universe. The universe had learned to build, not complex structures yet, but the first composite objects that were more than the sum of their parts. A helium nucleus isn't just two protons and two neutrons, it's a stable, unified entity with its own properties and behaviors. It was the universe's first lesson in architecture, its first experiment in creating something lasting from simpler components. As the cosmic kitchen cooled and the nuclear reactions ceased, the universe entered a new phase of its existence. It was now filled with a hot gas of hydrogen and helium nuclei, electrons and photons, all interacting in a dense, opaque plasma. The age of nuclear creation was over, but the age of atomic formation was still hundreds of thousands of years in the future. For now, the universe had to be patient, continuing its expansion and cooling, waiting for the right conditions to take the next crucial step in its journey toward complexity. After all that cosmic drama, the universe decided to take a very long nap. The era of nuclear cooking was over, the age of stars hadn't begun yet, and for hundreds of thousands of years, the cosmos entered what astronomers call the Dark Ages. It wasn't dark because there was no light, quite the opposite. The universe was so filled with light that it was completely opaque, like trying to see through a thick fog. But from our perspective, looking back through time, this period appears dark because none of that ancient light could travel freely to reach us. But before we drift into those dark ages, something quietly wonderful happened around 100,000 years after the Big Bang. The universe had cooled enough for the very first molecule to form. Not an atom yet, just a simple molecule, helium hydride, consisting of one helium atom and one hydrogen atom holding hands through a chemical bond. It was the universe's first tentative step into chemistry, its first experiment with the idea that atoms could work together to create something new. Helium hydride might not sound particularly exciting, but it represented a fundamental transition. For the first time, the universe had moved beyond nuclear physics and entered the realm of chemistry. Atoms were no longer just individual nuclear cores with their electron clouds. They could now share electrons, form bonds, and create molecular structures. It was like the universe had learned to write, and helium hydride was its first word. This first molecule was extraordinarily rare and fragile in the harsh environment of the early universe. But its formation marked the beginning of a new kind of cosmic evolution, one based not just on nuclear reactions, but on the more subtle dance of electrons sharing space between different atomic nuclei. Chemistry had been born, even if it would have to wait much longer to flourish. As the universe continued to expand and cool, it remained in a state that physicists call a plasma. All the hydrogen and helium nuclei that had been created during Big Bang nucleosynthesis were still separate from their electrons. The universe was like a cosmic soup where the ingredients, atomic nuclei and electrons, were all floating around separately instead of being properly combined into complete atoms. This separation wasn't by choice. It was because the universe was still too hot and energetic for electrons to settle down into stable orbits around nuclei. Anytime an electron tried to bind to a nucleus, forming a complete atom, an energetic photon would come along and knock it loose again. It was like trying to build a house during an earthquake. Every time you placed a brick, the shaking would knock it off again. This cosmic plasma had an important property. It was opaque to light. Photons couldn't travel very far before colliding with a free electron and being scattered in a random direction. Light existed throughout the universe, but it was trapped, constantly bouncing around like a pinball in a cosmic arcade game. The universe was bright, but opaque, like being inside a light bulb. Then, about 380,000 years after the Big Bang, something remarkable happened. The universe had finally cooled to about 3,000 degrees Kelvin, cool enough for electrons to be captured by atomic nuclei and stay captured. This event is called recombination, though technically it wasn't really a recombination since electrons and nuclei had never been combined before. It was more like the universe's first combination, its first successful attempt at making complete atoms. The transition wasn't sudden. It happened gradually over thousands of years. But once it began, it transformed the universe fundamentally. As electrons settled into orbits around hydrogen and helium nuclei, forming the first stable atoms, something extraordinary occurred. The universe became transparent. With most of the free electrons now bound up in atoms, there were far fewer particles available to scatter light. Photons could suddenly travel freely across vast distances without being constantly redirected. It was like a thick fog suddenly lifting, revealing a clear sky. The universe had learned to be see-through. This moment of first transparency released the most ancient light that we can observe today. All those photons that had been trapped in the cosmic plasma for hundreds of thousands of years were suddenly free to travel. They began a journey across space that continues to this day, carrying with them a snapshot of what the universe looked like at the moment it became transparent. We can still detect this ancient light today as the cosmic microwave background radiation, a faint glow that fills the entire sky. It's the afterglow of the Big Bang, stretched and cooled by the expansion of the universe from the bright, hot light it once was to the gentle microwave radiation we observe today. When scientists point their most sensitive instruments at any patch of empty sky, they can detect this primordial light, the first light that was ever free to travel across the cosmos. This cosmic microwave background is remarkably uniform, showing that the universe was incredibly smooth and homogeneous when atoms first formed. But it's not perfectly uniform. There are tiny temperature variations, differences of just a few parts in 100,000. These minute fluctuations are incredibly important because they represent the seeds of all the structure we see in the universe today. Those slightly warmer and cooler regions in the cosmic microwave background correspond to areas where matter was slightly more or less dense when the universe became transparent. The denser regions had a tiny gravitational advantage. They could attract matter more effectively and eventually became the sites where the first stars and galaxies would form. The less dense regions became the cosmic voids that separate galactic clusters today. In a very real sense, the cosmic microwave background is a baby picture of the universe, showing us what it looked like when it was just 380,000 years old. Every wrinkle and variation in that ancient light became a future galaxy, a future star, a future planet. The gentle fluctuations in temperature that we measure today became the cosmic architecture that shaped everything from galaxy clusters to the very world you're sitting on. The Dark Ages were ending, transparency had arrived, and the universe was preparing for its next great adventure, the formation of the first stars. Most of the universe, it turns out, is made of things we can't even see. This might sound like the setup for a cosmic joke, but it's one of the most profound discoveries in modern astronomy. The stars, planets, gas clouds, and galaxies that light up our telescopes and fill our photographs represent less than 5% of everything that exists. The rest of the universe is invisible, mysterious, and absolutely essential to the story of how we got here. The first clue that something was missing came from a brilliant astronomer named Vera Rubin, who in the 1970s was doing something that seemed quite ordinary, measuring how fast stars move around the centers of galaxies. What she found was anything but ordinary. The stars on the outskirts of galaxies were moving much faster than they should have been, given the amount of visible matter present. Think of it this way. If you watch a figure skater spinning with their arms extended, they spin more slowly than when they pull their arms in close to their body. The same principle should apply to galaxies. Stars far from the galactic center, like a skater's extended arms, should orbit more slowly than stars near the center. According to the laws of gravity, these outer stars should have been moving so slowly that they would take much longer to complete their orbits, or they should have been flung out into space entirely. But that's not what Rubin observed. Instead, she found that stars throughout the galaxy were all moving at roughly the same speed, as if some invisible hand was somehow providing extra gravitational pull to keep those outer stars moving fast enough to stay in their orbits. It was like watching ice skaters spinning with their arms extended, but instead of slowing down as expected, they were somehow maintaining their speed. Rubin's discovery was initially met with skepticism. Perhaps there was an error in the measurements, or maybe our understanding of gravity needed modification. But as more and more galaxies were studied, the same pattern emerged everywhere. Something invisible had to be providing the extra gravitational pull needed to keep those outer stars in their rapid orbits. Astronomers gave this invisible something a practical but unimaginative name: dark matter. Dark matter doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any way we can detect. You can't see it, photograph it, or touch it. It's transparent to everything except gravity, yet it outweighs all the visible matter in the universe by more than 5-to-1. It's as if the universe is an iceberg, and everything we can see, from the tiniest asteroids to the largest galaxy clusters, is just the tip floating above water. The implications of this discovery are staggering. Right now, as you listen to this, dark matter particles are streaming through your body by the billions. They pass through you, through the Earth, through the Sun, barely noticing that ordinary matter exists at all. In every cubic inch of space around you, there are probably thousands of dark matter particles, invisible and undetectable, yet collectively providing the gravitational foundation for the structure of the cosmos. Scientists have spent decades trying to catch these elusive particles. Deep underground, in abandoned mines and specially built laboratories, incredibly sensitive detectors wait patiently for the rare moment when a dark matter particle might interact with ordinary matter. These detectors are surrounded by layers of shielding to block out cosmic rays, radioactivity, and any other interference. They're kept at temperatures colder than outer space and monitored with exquisite precision. Yet after decades of searching, dark matter remains stubbornly invisible. During the Dark Ages we discussed earlier, while ordinary matter was slowly cooling and eventually forming the first atoms, dark matter was busy building the scaffolding of the cosmos. Unlike ordinary matter, dark matter doesn't get caught up in the electromagnetic interactions that can slow down or heat up particles. It responds only to gravity, which allowed it to begin clumping together much earlier than ordinary matter could. As the universe expanded, dark matter formed an invisible web of structure throughout space, creating gravitational wells where ordinary matter could eventually collect. When hydrogen and helium atoms finally formed, and the universe became transparent, these atoms fell into the dark matter scaffolding that was already waiting for them. It's like dark matter built the foundation and framework for cosmic architecture, while ordinary matter provided the visible decoration and detail work. This process accelerated the formation of the first stars and galaxies dramatically. Without dark matter's head start, structure formation would have taken much longer, and the universe might have remained smooth and featureless for billions of additional years. Dark matter didn't just help create the cosmic web we see today, it made it possible for stars to form early enough in cosmic history to create the heavy elements that planets and life require. But dark matter is only part of the invisible universe story. In the late 1990s, astronomers made an even more startling discovery. Two independent teams were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years. These supernovae served as cosmic lighthouses, allowing scientists to measure distances and the expansion rate of the universe with unprecedented precision. What they found defied all expectations. Instead of slowing down due to the gravitational pull of all the matter it contained, the expansion of the universe was speeding up. Galaxies weren't just moving away from each other, they were accelerating away from each other. It was as if someone had attached invisible rockets to every galaxy, pushing them apart faster and faster. This acceleration required some kind of anti-gravitational force, something that could push space apart instead of pulling it together. Scientists dubbed this mysterious influence dark energy, and it has turned out to be the most abundant component of the universe, making up about 68% of everything that exists. Dark energy is even more mysterious than dark matter. While we at least know that dark matter clumps together and provides gravitational attraction, dark energy appears to be spread uniformly throughout space and pushes everything apart. It's like a cosmic anti-gravity that becomes stronger as space expands, ensuring that the universe's expansion will continue accelerating forever. What could dark energy actually be? Scientists have proposed several possibilities, each stranger than the last. It might be the energy of empty space itself, a kind of quantum foam that exerts pressure on the fabric of space-time. It might be a new type of field, similar to the inflaton field that drove cosmic inflation, but operating much more gently over cosmic time. It might even be a sign that our understanding of gravity itself is incomplete and that Einstein's equations need modification on the largest scales. The discovery of dark energy was so unexpected that it overturned decades of assumptions about the universe's fate. Before the late 1990s, cosmologists debated whether the universe would expand forever or eventually collapse back in on itself in a big crunch. Dark energy settled that debate decisively. The universe will expand forever, growing colder and more diffuse until the last stars burn out and the cosmos fades into a cold, dark emptiness trillions of years in the future. The effects of dark energy are subtle on small scales. Within our solar system, or even within our galaxy, gravity is strong enough to overcome dark energy's influence. The Earth orbits the Sun, the Moon orbits the Earth, and our galaxy holds together just fine. But on the largest scales, between galaxy clusters separated by hundreds of millions of light-years, dark energy dominates. It's stretching space itself, making the universe larger and more spread out with each passing moment. Together, dark matter and dark energy have completely revolutionized our understanding of the cosmos. In the span of just a few decades, we've gone from thinking we understood most of the universe to realizing we can directly observe only a tiny fraction of what exists. It's one of the most humbling discoveries in the history of science, a reminder that the universe is far stranger and more mysterious than we ever imagined. When we add up everything in the universe today, the cosmic census looks quite humbling from our perspective. About 68% is dark energy, 27% is dark matter, and just 5% is ordinary matter, the stuff that makes up stars, planets, and people. We are living in a universe dominated by phenomena we barely understand, composed mostly of substances we cannot see or touch. This invisible universe isn't just an abstract concern for theorists, it's the foundation that makes our existence possible. The dark matter that surrounds our galaxy helps hold it together and influences the formation of new stars. The dark energy that accelerates cosmic expansion affects how galaxy clusters evolve and how the universe will end. We are intimately connected to these invisible components, even though we experience them only through their gravitational effects. It's a beautifully humbling perspective. Looking up at the night sky, we see points of light that represent a tiny fraction of what's actually there. The vast majority of the universe remains invisible, mysterious, and essential. We are like visitors in a vast, mostly invisible cosmic mansion, able to see only a few rooms while sensing the presence of something much larger surrounding us. We are made of the universe's rarest ingredient, ordinary matter, living in a cosmos dominated by the invisible and the unknown. This invisible architecture has brought us to the modern universe, where ordinary matter has finally had enough time and the right conditions to organize itself into the rich complexity we see today. After 13.8 billion years of cosmic evolution, here we are. From that inconceivably small, impossibly hot beginning, the universe has grown into something magnificent and vast, filled with galaxies and stars, planets and moons, and at least one world where curious beings can look up at the night sky and wonder how it all began. We've journeyed from the Planck era to the present moment, from quantum foam to cosmic webs, and the transformation has been nothing short of extraordinary. Today's universe bears little resemblance to its infant state. Where once there was perfect unity, now there is beautiful complexity. Where once there was a single unified force, now there are four distinct forces, each with its own personality and role to play. Where once there was only the simplest matter, now there are 94 naturally occurring elements, countless molecules and structures ranging from DNA to gas giant planets to superclusters of galaxies. The cosmic census we conduct today tells a remarkable story. The universe is composed of roughly 68% dark energy, that mysterious force that's accelerating cosmic expansion. 27% is dark matter, the invisible scaffolding that holds galaxies together and guided the formation of cosmic structure. And just 5%, a humble sliver of the cosmic pie, is ordinary matter, the stuff of stars and planets and people. That 5% might seem insignificant, but it's the most interesting 5% in existence. This is the matter that can emit light, absorb light, undergo chemical reactions, and organize itself into the incredible complexity we see around us. It's the matter that can become self-aware, ask questions about its own origins, and even write gentle bedtime stories about cosmic history. Within that 5% of ordinary matter, the universe has become remarkably creative. Stars have learned to cook heavy elements in their cores, forging carbon and oxygen and iron through nuclear fusion. When the most massive stars reach the end of their lives, they explode as supernovae, scattering these newly minted elements across space like cosmic seeds. These elements then collect in new star-forming regions, creating planetary systems where rocky worlds can form. On at least one of these rocky worlds, and possibly on countless others, the universe has achieved something truly remarkable. self-awareness. Through billions of years of evolution, cosmic matter has organized itself into forms capable of contemplating their own existence. We are the universe looking at itself, composed of elements forged in stellar cores, asking questions about the very processes that created us. The structure of today's universe is a testament to the power of small differences amplified over vast periods of time. Those tiny quantum fluctuations during inflation, smaller than subatomic particles when they formed, have grown into the cosmic web of galaxy clusters, filaments, and voids that we observe today. The largest structures in the universe can trace their ancestry back to microscopic variations in the primordial quantum foam. Galaxy clusters now span millions of light years, held together by dark matter's gravitational embrace. Within these clusters, individual galaxies like our own Milky Way contain hundreds of billions of stars, many of which host planetary systems. The scale of it all is staggering. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth, and each star represents a nuclear furnace that has been burning for millions or billions of years. The elements that make up your body have traveled an incredible journey to reach you. The hydrogen in your water was forged minutes after the Big Bang during primordial nucleosynthesis. The carbon in your cells was created in the core of an ancient star that lived and died before our solar system even existed. The iron in your blood was manufactured in a stellar explosion that scattered its atomic gifts across interstellar space, where they eventually found their way into the cloud of gas and dust that collapsed to form our sun and planets. You are, quite literally, made of star stuff, as astronomer Carl Sagan memorably put it. But more than that, you are made of universe stuff, atomic matter that has been on a journey spanning nearly 14 billion years of cosmic history. Every breath you take contains atoms that have existed since shortly after the Big Bang, atoms that have been part of countless stars, planets, and perhaps other living beings before finding their way to you. The universe today continues to evolve, though at a more sedate pace than in its early, dramatic moments. Stars are still being born in gas clouds throughout the cosmos, though at a much slower rate than in the universe's youth. Galaxies continue to merge and interact, creating new structures and triggering fresh bursts of star formation. Black holes grow as they consume matter, occasionally merging with each other in events so energetic they create ripples in space-time itself. But the universe's expansion continues to accelerate, driven by dark energy's mysterious influence. This means that in the far future, billions of years from now, galaxies will become more and more isolated as space itself stretches between them. Eventually, the universe will become a much lonelier place, with individual galaxies separated by such vast distances that beings living in one galaxy won't be able to see any others. For now, though, we exist in what might be called the universe's golden age. Stars are still shining, galaxies are still interacting, and cosmic evolution continues to create new possibilities for complexity and beauty. We live at a time when the universe is old enough to have developed rich chemistry and complex structures, but young enough that it's still vibrant and energetic. As you drift towards sleep tonight, consider the extraordinary journey that brought this moment into existence. From the quantum foam of the Planck era to the gentle rhythm of your breathing, from the first separation of forces to the formation of the thoughts flowing through your mind, the universe has been engaged in an epic story of creation and evolution. And somehow, improbably, wonderfully, that story has led to you, here, now, participating in the cosmic adventure simply by existing. The universe began with nothing and became everything. And part of that everything is this quiet moment, this gentle story, this peaceful drift toward dreams filled with stars. And so, we arrive at the end of our cosmic journey, though really, the universe's story continues all around us. From that first impossible moment to the gentle rhythm of your breathing, we've traced a path through 13.8 billion years of cosmic history. Every atom in your body, every breath you take, every thought drifting through your mind, all of it born from that ancient spark of creation. We've wandered through the hottest temperatures ever reached, watched forces split apart and come together, seen matter win its battle against antimatter, and witnessed light finally break free to paint the cosmos. And somehow, improbably, wonderfully, all of that cosmic chaos and creation led to you, here, now, peacefully listening to stories about the stars. Tonight, as you settle into sleep, you're made of hydrogen forged minutes after the Big Bang, carbon cooked in the hearts of ancient stars, and countless other elements scattered by supernovae across the galaxy. You are, quite literally, a collection of cosmic stories, a walking piece of the universe's biography. If you found any peace in this gentle expedition through space and time, if the wonders of creation helped you drift toward dreams, we'd be honored if you follow us for more quiet journeys through science in the future. Thanks for joining us here at Sleep Science. Sleep well.